flow and modeling. Hello, welcome to you all on today's webcast session on turbulent flow and modeling being organized by IIHR, Institute for Integrated Hydro Environment Research. My name is Rakesh Kumar Chaudhary, working as a CEO at IIHR. Beside this, I am also working as a lecturer at IU Thapdal campus as an adjunct faculty. We have been actively involved in research and innovation on hydro environment research matters. Before this, we successfully conducted webinars and trainings on different topics and software relevant to water. Before this, previously we have conducted training on HECRAS, hydrologic data management. Similarly, we did a webinar on graduate study abroad and so on. Uh, Beside this, we have also involved in research works. We have published numerous several research papers, and I think our team citation is more than 200. Uh, and we are thinking about the why not to conduct the study, the webinar on the turbulent flow. So we have decided to conduct the webinars on turbulent flow. We know that the turbulent flow has become a fascinating topic today in today's world. It is ubiquitous in nature, encountered in a wide range of natural and engineering systems, such as atmospheric boundary layer, flow through river canals, ocean currents flow over transport system, flow through all types of fluid masses, etc. I think we should be able to get some usable estimate of such flow using numerical simulations or theoretical means. The accurate or approximate estimation of flow parameters need to be accurately model the turbulent flow, which is a part of mean flow, and most of the problems either in river engineering or any field related to fluid depends on how we can accurately model the turbulent flow. Since turbulent is one of the prime factors for any flowing systems on which multiple physical outcomes depends, whether it is scour, sediment transport, diffusion, aeration, energy dissipation, drag force, or shear stress. Therefore, today we have invited presenter Ankit Gautam as a key speaker on the topics. Now, I would like to introduce Mr. Ankit Gautam. Ankit Gautam is a graduate student in the mechanical engineering PhD program at Utah State University and a member of the experimental fluid dynamics lab. He's, uh, he did a bachelor's and master's in mechanical engineering from Tribhuvan University in 2021. Uh, his research interests include fluid dynamics with a specific focus on turbulence and shear flow. He is currently investigating the dynamics of inertial particles interacting with turbulence and gravity. Before coming to USC, Utah State University, he worked as a mechanical design engineer in a hydropower company. Uh, Alongside his academic and professional endeavors, he loves to talk about history, religion, and psychology and astrology. Uh, I, in this presentation, Mr. Ankit Gautam will talk on this topic in detail. After the presentation, we shall go for the panel discussion where we have invited six panelists. Uh, we will introduce them later. Uh, if there is any questions from our audience, then this question will be directly asked to the panelist experts invited, and then we will conclude our discussion. So, if you have any questions, type in the message box. Now I would like to welcome Mr. Ankit Gautam. Welcome, Ankit sir.
Hi. Now I am going to start the presentation because we have limited time.
Okay, sir. Please
Yeah.
proceed. You can share your screen, I think.
My presentation is on a brief introduction on turbulence and turbulence modeling. Now I am going to start the presentation. First, the turbulence was studied by the Leonardo da Vinci. He already observed that sometimes the fluid flow seems to be degenerate into what looks like a random motion. Observe the motion of the surface of the water, which resemble that of air, which has the two motions of which one is caused by the weight of the air and the other by the direction of the currents. Thus, the water has eating motion, one part of which is due to the principal current and the other to the random and reverse motion. Then the turbulence was studied on the basis of Renault's uh, Osborne Reynolds found that if the viscous force dominated the full stage laminar, when the inertial force that the non-linear term being to dominate for transit to the turbines. And then he characterized the balance using the Reynolds number. Reynolds number is the ratio of the inertial force to the viscous force. All four become unstable above a certain Reynolds number. A simple one are a two-dimensional jets, wake, pipe, fat, weight, boundary layer, and other are more complicated three-dimensional flows. There is a transition between a laminar and a turbulent flow when the Reynolds number get increased. Uh, how can we define the turbulence? Is the flow turbulence? How can we know that? Along the surface in external flow, when the streamwise Reynolds number is greater than 5 into 10 to the power 5, or in around the obstacle when the Reynolds number get more than 20,000, or internal flow where the Reynolds number get more than 2,300. These are factors in terms of Reynolds number when the flow become turbulent flow. Other factors such as pre-stream turbulence, surface condition, and disturbance may cause a earlier transition to the turbulence flow. What is turbulence? Chaotic and random states of the motion develop in a flow, and it is termed as a turbulence. In the turbulent flow, the velocity and pressure changes continuously with times. The velocity fluctuation give rises to the additional stresses on the fluid. A streak of dye which is introduced at a point will rapidly break up and the disperse. This is a simple example when something is passed in the turbulent flow. The turbulent flow give rise to the high value of diffusion coefficient for a mass, momentum, and a heat. These are some characteristics of the turbulent flow. Turbulent flow always occur at high Reynolds number. They are caused by the complex interaction between the viscous terms and the inertial terms in the momentum equation. One characteristic of turbulent flow is their irregularity or randomness. A fully deterministic approach is very difficult. Turbulent flows are usually described statistically. Turbulent flows are always chaotic, but not all chaotic flows are turbulent. The diffusivity of turbulence causes rapid mixing and increased rate of momentum, heat and mass transfer. A flow that looks random but does not exhibit the spreading of velocity fluctuation through the surrounding fluid is not turbulent. If a flow is chaotic but not the diffusive, it is not turbulent. Turbulent flows are dissipative. Kinetic energy gets converted into heat due to the viscous shear stresses. Turbulent flows dies out quickly when no energy is supplied. Random motion that have significant viscous force, such as random sound wave, are not turbulent. Turbulent flows are rotational, that is, they have a non-zero vorticity. Mechanisms such as the stretching of three-dimensional vortices play a key role in the turbulence. Turbine have a different structure and its properties is mainly dependent on the mean flow. In the turbine flow, there are rotational flow structure called the turbine DDs, which have a wide range of the length scale. The characteristic of length scale will be presented in next slide. And in the stagnation, in the turbine flow, there are stagnation point, recirculation region, Horseshoe vortices, and Karman vortices. This is the type of the turbine flow In the turbulent flow, the main thing in the analysis is the Renault decomposition for turbulence. Renault's purpose of a very indigenous idea and right the velocity is the sum of the mean flow in a turbulent departure from the mean. Uh, He then split the Navier-Stokes equation along this line to get a one equation from mean and another from the turbulence. Here, what is U dash? The U dash is the variational component from the mean. If we want to measure the turbulence or turbulence intensity, we usually measure in the uh, variation, which is the standard deviation from the mean flow. And similarly, the horizontal velocity and the all three-dimensional velocity along with pressure and density are discretized into the mean component and variational component. Uh, this is a simple figure in the turbulence in the river flows. Uh, in the river, the turbulence get introduced when the uh, go through small section. In the small section, when the cross section becomes small and the velocity become high, then it will create a turbulence. Turbulence can occur around the borders, and the turbulence can occur in the falls. Uh, Now I want to go through the scales of the turbulence, which is a more important thing that to be studied in turbulent flow. In the turbulent flow, there are three different scales. Here you can see the picture there
mm,
uh, that there are three different scales. The pink are a large scale, which are energy production scale. The red one are inertia scales, which are the medium size scale. And the blue are the which are a small scale, and they are a dissipation scale or a small scale. Uh, th- Now I want to go through this characteristic of the different scales of the turbulence. First, I want to go through large scale, which are also known as energy production range. This energy production range or large scale are affected by the boundary condition in our flow specific. They interact with the mean flow, transform the mean kinetic energy into turbulent kinetic energy. They produce almost convective and advective flux. They have a large ET Reynolds number, and the large scale are high anisotropic and the fluctuation are different in different direction. And now inertial sovereigns or which are known as the intermediate scale. This scale does not interact directly with the boundaries or mean flow and are flow independent. They receive the cascading turbulent kinetic energy and passes it on to the smaller scale. Turbulence is homogeneous and isotropic according to the Kolmogorov theory. Now the smallest scale or dissipation scale are the scale which does not interact with the boundaries or a mean flow and are flow independent. They dissipate they dissipate all the turbulent kinetic energy heat, no source heat energy. The smallest turbulent scale is called the Kolmogorov scale. Here we can see the picture of the energy spectrum. Yeah, in the schematic illustration of production, uh, energy cascade and dissipation in the energy spectrum. The high amount of energy is carried by the large scale, and the dissipative energy is carried by the small scale. And then Kolmogorov statically describes the main feature of the smallest turbulence scale known as Kolmogorov microscale is the length scale. This uh, uh, these are related with the time scale and velocity scale, and they are shown here, and how they interact with uh, dissipation and viscosity. He- Here,
mm,
the process of changing from small scale large scale to small scale is through a vortex stretching. And the vortex stretching is the lengthening of vortices in a three-dimensional fluid flow, which is associated with a corresponding increase of component of vorticity in a stretching direction due to the conversion of the angular momentum. Vortex stretching is at the core of the description of the turbine's energy cascade from the large scale to the small scale in turbines. In this way, the kinetic energy is handed down from large eddies to the progressively small and smaller eddies in which is termed as the energy cascade. Here in the figure, it is shown that the homograph 5 by third law. This law states that in the inertial range, the energy cascade depends only on the size of the eddies. In the significant experiment, evidence support the inertial cascade as Reynolds number, and this is verified by the many experiment uh, which were conducted in the past research. Now that now I want to go through the turbulent boundary here, and this is important not only in the theory but also in the modeling aspect. As the turbulent as the boundary here provide the main aspect of designing and modeling turbine system. Turbine boundary layer consists of the four regions. Viscous of air, which is a very thin layer next to the wall where the viscous effect are dominant. The buffer layer, in which the turbulent effect are increasing, but the flow is mainly dominated by viscous effect. The logarithmic layer, in which the turbulent effect are much more significant. In the logarithmic region are denoted by the equation which is shown here. And this is a popular equation while dealing with the turbulent boundary layer. And another is the outer layer in which the turbulent effect dominates over the viscous effect. The term boundary layer thickness is usually introduced in the turbulent boundary layer. Boundary layer thickness is the vertical distance from the wall to a point where the flow velocity reaches 99% of the free stream velocity. The different turbulent flux term used in the turbulent flow are shown here. And the first term is the effect of turbulence on the mean flow, which is a product of the variational velocity in two directions. And next one is a turbulent stress applied on the mean flow. Acts almost like a very strong viscosity. And third term is the effect of turbulence on the mean in temperature field. And fourth term is the turbulent heat flux act almost like a very strong diffusivity. Uh, Similarly, the fifth term, which I introduced, is about the concentration in which the turbulence flux of pollutant water vapor. Uh, and the reason of why the turbulent flux terms are important. It is because many models cannot solve the full equation. They are too demanding computationally. They solve the mean equation only. But in this equation, we have this additional unknown, the turbulent flux, that we need to model. Turbulence closure problem. At the surface, these turbulent fluxes are the wall stresses, flux of heat, water vapor, momentum formed in the surface of the fluid. We need to model a special surface closure or measure them near the wall to describe the fluid interaction. These are the important term in the parameter that is used in the turbines. Taylor microscale. Taylor microscale is a length scale that characterizes the size of the large energy containing eddies in a turbine flow. Entropy. It is a measure of the rotational energy per unit mass in a turbine flow. It is related to the intensity of vortices. Turbine dissipation. It is the rate at which the turbine kinetic energy is converted into internal energy or heat energy due to the viscous effect in the fluid. Integral length scale. A length scale characterizing the size of the large eddies in a turbine flow. It is often used in the context of describing the spatial structure of turbines. And now, why do we care about the turbines? And the turbines is mainly uh, used in many fields, such as aerodynamics in aviation, to find the performance and stability of aircraft, efficiency in engineering, weather prediction and climate modeling, uh, especially in energy production in hydropower and wind energy plant, environmental impact, heat transfer in engineering, environmental fluid dynamics studies, biological flow, and these are many field where the turbines is used. In not only in this field, but there are many other field where the turbines can be used. But this consists of the main core area where the turbines is used. Now I want to go to the modeling of the turbines. Why we want to model the turbines? Direct numerical simulation of governing equation is only possible for several Reynolds number 4. Instead, we solve the Reynolds number Navier-Stokes equation. You can see the equation in the slide. And here we want to model the Reynolds stress. The main part of the modeling of the turbines is modeling the Reynolds number. How we can take the effect of Reynolds stress from the flow to our numerical model. Time average statistic of turbulent velocity fluctuation are modeled using functions containing empirical constant and information about the mean flow. Large eddies simulation numerically resolve large eddies and model small eddies. How complex the flow? How do we know the complexity of the flow? The complexity of the flow can be known through the extra strain rate, which are through the streamline curvature, lateral divergence, acceleration or deceleration, slowing effect, recirculation or separation, and secondary flow. 3D perturbation, transpiration, blowing out a suction mechanism, free stream turbulence, interacting zero. These are a different aspect how the flow can be made complex. How can we make our for, choice for a turbulence or a turbulence model? First, we have to consider the flow physics, computational resource what we have. Then we can go through the turbulence model in near treatment. The near treatment is the most important thing what we get from the effect because it tests the effect when interacting with multi-phase flow, like from air to solid or water to solid. Like, mm. And we want to apply flow physics into inner turbulence model into computational grid. In this way, have to have how to take a choice. Now I want to go through turbulent modeling approach. There are a different turbulent modeling approach. These are zero equation model, one equation model, Sparta-Amorous model, two equation models, standard K epsilon models, RNG K epsilon model, realizable K epsilon model, Reynolds stress model, RZD simulation, direct numerical simulation. These are a popular numerical tools that are used for the turbulence modeling. Apart from large ET simulation and direct numerical simulation, all of them are a range-based model. And uh, in the numerical model that are enclosed in the black box are available in the popular software called ANSYS in the ANSYS 5. The main thing that we have to consider is the increased computational cost for iteration. Like shown in the picture, The range-based model are shown that they can do very well if we use in a most useful research. For example, the DNS shows the accurate model while range shows the less accurate study of the model. Because the RGT simulation and direct numerical simulation include more physics comparative to range-based model. That can be seen in the figure that is attached here. Uh, One equation model or a Sparta-Alvarez models is designed specifically for aerospace application involving wall-bounded flow. Boundary air with adverse pressure gradient in a turbomachinery. One equation model can use a coarse or a fine mesh at well. It is designed to be used with a fine mesh as a low Reynolds number model throughout the viscous affected region. Uh, this is sufficiently robust for relatively crude simulation on coarse meshes. And second model is two equation model, which is known as standard K-epsilon model. It is the baseline models of the two equation model. It is most widely used model in industry. It is well researched and its strength and weakness are well documented. In the semi-empirical method, K equation derived by subtracting the instantaneous mechanical energy equation from its time average value. Epsilon equation from the physical reasoning. In this equation model, there are many equations, and we have to change the parameter according to the physics of the flow, and we have to make a choice how we can change the parameter of the flow, and what is more important. We have to add these terms, and that's why we get a different equation model. And these equation models are valid only for fully turbulent flow. These models have a reasonable accuracy for a wide range of the turbulent flows in industrial flows and heat transfer flows. Uh, Realizable KF model. It shares the same turbulent kinetic energy equation as a standard KF model. It is its superior preference for flow involving planar and round jets, boundary air under a strong adverse pressure gradient separation, rotation and recirculation, strong streamline curvature. It is a RNG KF model. KF equation are derived from the application of a rigorous statistical technique, renormalization group method to the instantaneous Navier-Stokes equation. Similarly, in the form to the standard K epsilon naught equation, but include additional term in E equation that improve analysis of rapidly strained flow, the effect of through and turbulence, analytical formula for turbulent Prandtl number, differential formula for effective viscosity. It's improved prediction for high streamline curvature and strain rate, and for transitional flow involve heat and mass transfer. Renault stress model. Renault stress model poses the Renault average Navier-Stokes equation by solving additional transport equation for the Renault stresses. In this model, transport equation derived by Renault averaging the product of the momentum equation with the fluctuating properties. Closure also require one equation for turbulent dissipation. Isotropic eddy viscosity assumption is avoided. Resulting equation contain terms that need to be modeled. Renault stress model has high potential for accurately predicting complex flow. These complex flow account for streamline curvature, sway, rotation, and high strain rate. These some example of this type of the flow are cyclone flow, swaying compressor flow, rotating flow passes, and secondary flows. Large dissimulation. where cities are main responsible for transport of momentum, energy, and other scales. They are directly affecting the mean field. Anisotropic subjected to history effect in four dependent. I strongly dependent on four configuration, boundary condition, and four parameters. In the small entities which tend to be a more isotropic and less four dependent, more likely to be easier to model than large entities. Large entities simulation directly compute result large entities in models on small entities. Large computational effort required. A number of grid point is directly proportional to the screen friction based Reynolds number. Here is RE Utah, which is known as a screen friction Reynolds number, and also in the unsteady calculation. The important aspect of turbulence model is a near treatment of the turbulent model. Most caves not in the renal stress model, turbulence model will not predict the correct near-wall behavior if integrated down to the wall. A special near-wall treatment is required. A standard wall function, non-equilibrium wall function, a two-year zonal model. These are the special near-wall treatment required for turbulent modeling. The nearby boundary area structure turbine model depend on the wipers value. Uh, uh, Under the wipers value of 5, it is a viscous subwear. In between 5 to 60, it is buffer wear or a bending region. For wipers greater than 60, it is fluid turbulent region or a log region that we discussed earlier. And there are upper in the upper limits that for a Reynolds number. This is a comparison of the three near wall treatment area, which are standard wall function, non-equilibrium wall function, and two-year zonal model. First, standard wall function have a strength that it is robust, economical, and reasonably accurate. Its weakness is that empirical based on the simple high Reynolds flow, poor flow rate, low Reynolds number effect, massive transformation, uh, and pressure gradient, strong body forces, and I 3D flow. Non-equilibrium wall function account for a large pressure gradient effect, also the non-equilibrium separation reattachment and impingement. Non-equilibrium wall function model have a poor for Reynolds effect, massive transpiration, severe pressure gradient, strong body forces in IA3D4. A two-year zonal model. It does not rely on law of the wall. It is good for complex flow, especially applicable for Reynolds flow. Its weakness is that it requires a finer mesh resolution and therefore larger CPU and memory resource. This is a weakness of the two-year zonal model. And thank you. I want to end this presentation.
Thank you, sir. You have nicely explained about the turbulent flow, Reynolds decomposition, and scale of turbulence, Kolmogorov scales, how the turbulent fluxes evolved from the Reynolds decomposition and turbulence modeling approach, and differences and different types of turbulent models and its application. Now I will take some questions from the audience, and then we will ask these questions with the panel. That is the panel discussion. Now we have invited six panelists, and I would like to introduce them and also welcome them. The first one is the Naresh Swal. He did bachelor's from the Tribhuvan University and master's from Hawaii University, then PhD from Louisiana. He is currently doing PhD at Louisiana State University. His area of interest is environmental flows, hydrology, and irrigation. Similarly, the second panel member is Khem Prasad Bhatrai. Currently, he is doing Mm. Currently, he's doing he did masters from Hawaii University, and currently he's doing PhD at Colorado State University. His area of interest belongs to advanced fluid mechanics, turbulent flows, hydropower, water hammer, and surges. Similarly, the third panel member is Kamal Prasad Pandey. He also did a B in civil engineering from Tribhuvan University, masters from Hawaii University, and currently he is doing PhD at ETH Zurich, Switzerland. His area of interest is eco-hydraulics, fish passes, and turbulence. Similarly, the fourth one member is panel member is Ravi Kumar Misra. He did B in civil engineering from Punjab Engineering College, PEC, and MTech from IIT Roorkee in hydraulics. And currently, he's doing PhD at IIT ISM Dhanbad. His area of interest is hydraulic structures, piano keywear, sediment transport, and river modeling. Similarly, the fifth panel member is Pratyush. He did B in civil engineering from JNTU, Kakinada, India, and masters in earthquake engineering from IIT Roorkee. He's also the department topper. Currently, he's working as a bridge design engineer, as well as he is a director of public relations at IIHR. And the last our panel member is Ishwar Joshi. He did bachelor in civil engineering from Tribhuvan University and masters from Hawaii University in water resources, and currently he is doing PhD at Utah State University. His area of interest is sediment transport, river modeling, and fluvial hydraulics and hydrology. Now I will take some questions from the audience, and if there is no any questions, then I will try to facilitate this discussion with some questions I have collected. And so my first question is to panel members, Kamal Prasad Pandey. What is the sir Kamal sir? What is the difference between the vortex and eddies in turbulence?
Namaste, everyone.
Namaste.
S- So I am here, Kamal.
Yeah,
So it's good to see you all here. And yeah, thank you, Rakesh sir, for the questions.
yeah, yeah.
So yeah, there there is a fundamental difference between the vortex and eddies. If we are talking about the turbulence, we are usually talking about the eddies that are generated in the turbulent field. But there is a little bit of distinction between the vortex and eddies in terms of how they are like defined. So a vortex is a swirling mass of fluid or air that rotates around the center of a low pressure zone.
Okay,
So it's like a mathematical closed region, so which is created due to the low pressure, and
okay,
it is characterized by a circular motion and can exist independently of external forces. So it
okay,
may occur independently of external forces, but if you talk about the eddies, they are just the circular motion of the fluid that runs counter to the main flow. So the eddies are generated in the turbulent field, but when you observe those eddies clearly, you can observe that those eddies are generated and they seems to be traveling in opposite direction of the flow. It's like the retrograde motion of the planets. It's actually moving downstream, but when you observe it carefully, you feel like that they are moving counter to the flow. So it
uh,
is created by a disturbance in the flow.
okay, sir.
So
I will try to stop you here because we have very much less time. Now, I would like to
okay.
add one more questions. What is the difference between chaos and turbulence? I think uh, Ankit sir will answer these questions. Ankit sir.
Yeah, like chaos is the type of the disturbance, and turbulence. It is not only chaos, but it is also a diffusion.
Okay.
Uh,
Thank you, sir.
and
Okay. Okay, sir. Now I would like to add one more question.
Uh,
What kind of instruments can be used to detect the energy at inertial subbrains and determine the future of energy cascade line as you have shown in the slide 12
mm,
and 13?
mm,
So
yeah,
can you please explain it?
yeah. This is a good question.
Mm.
And in the tournament, we first measure the different velocities from different instrument like anemometer or PIV. In this, we divide the section of the flow into the main grid point, and we calculate different velocity, and we identify the mean velocity in the variational velocity. After this, we calculate the energy spectrum in different range. Uh, it is like a mathematical process. After finding the correlation effect in the turbulent flow, this will help to determine the range of high scale, medium scale, and low scale in the energy spectrum.
Okay, sir. Thank you, sir. Now my next question is, how is time scale captured in turbulence? As we know, turbulent flows are not only spatially varying, but also varies in time. Like the one shown from ADV measurements, where ADV measures at single point is long time. We see a variation according to the elapsed time in your slide 17. Could you please explain it?
Is it based on the side?
17. How is time scale captured in turbulence?
Which
Uh,
side?
Slide 17, I think. Yeah. Mm. As we know, turbulent flow are not only spatially varying, but also varies in time, like the
Uh,
ones. Okay. Uh,
uh, it is a process of measurement along the time. It is a spatial and a temporal variation. Temporal variation is measured with different time scale. Uh,
okay.
uh, we have to define a different time scale, and then we have to calculate the dissipation rate. And with the help of the dissipation rate and viscosity, we measure the time scale of the turbulent flow.
Okay, sir. My next question is uh, to Kamal, sir. Turbulence always have negative effects. Can you explain, sir, Kamal, sir? Hello, Kamal, sir. Uh, so I think Ankit, sir, will. Mm, uh, Sir, can you just put your views on what is it has always its negative effects or
Yeah,
somewhat.
actually, the turbulence carries the turbulent kinetic energy into the dissipative energy, which
Mm,
goes away through the heat energy or it dissipated eventually when the viscous
mm,
effect become
mm.
dominant. That's why this energy cannot be used for general purpose. The turbulent kinetic energy is like a waste of energy. That's why it create a negative effect.
Okay. My next question is on, can you tell about the DNS approach and can the new generation of computing process like machine learning and AI solve the turbulence problems? Ankit sir?
Uh, uh, artificial intelligence is the based on the probability concept. Like if the
Mm,
result is in the probability certain probability range, then it will say yes or no uh, in the basis of machine learning. In the way research studies, we can use a machine learning approach, and in the DNS studies, it is with the effect of the physics. If the physics say yes, it will say yes. In the DNS require a high range of the computational resource, and that
mm,
because in each step of the model, it have to store a large amount of the data, and that we need a high computational resource. If we incorporate machine learning and DNS,
Hmm.
and then it will make it easy for the DNS models to implicate, or it will reduce a certain amount of computational cost in future.
Okay, sir. Then the next question is, I think, Iswar sir, I would like to answer this question to from the Iswar sir. Which simulation model is better for which purpose? For example, we have DNS, LES, and RNS modeling approach. So, which is better, Iswar sir?
Yeah, thank you, Rakesh sir, for the question. It, it depends. It doesn't depend on like which one is better. It's about the computational resource you have and the type of problem you want to solve. For example, if the problem or the domain of the interest is too big, like of kilometers, like if you say in the context of rivers, if it's like kilometer, then you cannot think about like direct numerical simulation or large or even large edge simulations. In that case, the third one would be better. But when you want to have like very special like very you want to study very small phenomena, for example, okay, what is the flow over where, then maybe in that case you can use like direct numerical simulation where it will be cost efficient, and then you can have the very detailed flow properties, also like detailed characteristic on the boundary layer, so which can enhance the like Reynolds average models or all empirical equations or something like that. I can give you a very good example in context of like large edge simulation, but not that was not DNS. Like when the flood it breaches the bank, or when we have like um, um, you mean like the bank will discharge greater than bank will discharge, then there is a very interesting phenomena where there is like reduction of main channel velocity, and there is transfer of lateral moment on the floodplain. So there has been research where large edge simulation has been used there to determine, okay, how there is certain decrease in velocity in the main channel, and like how it impacts the flow properties in the during the case when flood happens. So it depends on the problem. It's not like which you want to use.
Okay, sir.
um, so I think
Okay, okay, sir.
that's my perspective. Yeah,
Yeah, yeah.
thanks.
Uh, Ravi, you have do you add anything more on this question? Ravi, Mister,
Yes.
could you
Right
would you
now,
like to? Yeah, yeah.
not in that question, but I would like to talk
Hmm,
about this turbulence modeling in the
hmm.
field of sediment transport, right?
Yes, yes.
Because
Okay.
sediment, when we are talking about multi-phase flow, where we are also talking about sediments and water, and then there is of course air, right?
Hmm,
This it becomes more complicated, like choosing the model, choosing the type of model. When we are talking about direct numerical simulation or large area simulation, it becomes very much computationally intensive when it comes to
hmm,
the sediment transport modeling, right? Especially when we are modeling river systems. Suppose we take any portion of the river and we try to account for the flow around hydrodynamics and both sediment model. So it becomes very computationally intensive when we go for large eddy simulation. So I would like to ask
hmm,
Mr. Ankit,
hmm.
uh, how can we choose the model, especially in these kind of problems where we also need accuracy. At the same time, we are modeling like particles which are in some like when we are modeling sediment, we are talking about 1 or 2 sized particles, right? So size is also important, accuracy is also important, and yet we want to be more computationally less intensive so that we can increase our efficiency. So how can we choose a suitable model for that?
Ankit, sir.
Yeah. Especially in a multi-phase flow, there is no direct numerical model that we want to apply. Uh, First, it is based on the experimental studies. And second, if we want to choose the numerical model for accuracy, we have to mainly see the condition of the flow, uh, especially the ratio between the density, the parameter such as density ratio. How is the density of particle comparative to density of fluid? For example, density of sand to density of water. And in the year four, which was a different model in my university and college, we are using the RGD simulation model to find the movement of the particle in the year four. And similarly, if we do not have the large resource for RGD simulation in river, then we have to base on the Reno's range-based model. And first, if we have computational resource, we can go through the RGD simulation because that is the main thing that we can go through the sediment transport model.
Okay, sir. Now I would like to add one more question.
Like
Uh,
I can
yeah.
like interrupt here. So
Okay, okay,
like
sir.
I also heard like maybe if Ankit sir knows or any other panelist they know here,
Hmm.
like there's a recent new trend of like graphical GPU processing unit in numerical models. Like, does that add to any values like to increase the efficiency during computation? If anybody knows here, for example, if you are simulating a river that's like kilometers of kilometer, then if you need very fine grade, and then if you use GPUs, then CPU, then it happens like the computation is quite faster. So I don't know much about that, but just I think this is a recent trend I have seen in research. So, like, does anybody know here, like, if like turbulent properties are also incorporated in at that in such scenarios? Maybe just a
Okay, sir.
question. Yeah, it's for interaction. Yeah. Mm.
Okay, sir. I would like to add one more question
Yeah.
to Ankit, sir. Every numerical model involves empirical numerical constants which are obtained by validation with experimental data and may not be universal for all turbulent flow. So, how can we address these types of problems to accurately model the turbulent flow of our interest?
First, we have to study the physics of the flow,
Yeah.
and like there are different boundary conditions, and we have to identify how the this type of constant will affect our result. If we want to study the boundary layer flow, then the boundary layer parameter will be more important.
Hmm.
If our flow is away from the boundary and it depends on the mean flow, then we have to go through that.
Hmm.
And this type of things we have to consider while determining the constant.
Hmm. Okay, sir. Uh, One more question. The additional term Reynolds stress obtained from Reynolds decomposition, how differ from the actual shear stress imposed by fluids?
Mm, Actually, the Renault stress is the variation of the flow. While calculating the exact stress in laminar flow,
Yeah.
it is based on the velocity and viscosity. What
Okay.
in turbulence flow, which is the Renault stress,
Hmm.
it is dependent upon the variation of the flow from the mean flow.
Yeah.
It is a product of the different variational velocity throughout
Hmm.
the flow.
Okay. Okay, sir. Kamal, sir, I would like to ask you one question. What are the interesting turbulence research area and its and application in Nepal? Could you please explain, answer it? Kamal, sir?
So in Yeah, so in context of Nepal, we have different kind of problems. So some of them are related to the river, some of them are related to the hydropowers, and some of them are related to the ecological. So I can give you a good example. So there has been many research in field of turbulence where they are used to model certain kind of the habitat where fish and other organisms live, and the scientists they want to see the turbulent properties of those region where the fish and other microorganisms prefer to habitat. And what they do is like if you see like there has been research in salmon which state that they like to spawn in a habitat where there is more gravel. But if in a river system, if there is no dynamic flood or something like that, then what happens in long run, the fine sediment may get trapped over the coarse sediment. It's called river harmony in geomorphological term. And then you may have like a deposit of very fine layers which makes your bed more smooth, and the salmon they may not like it. So to agitate those particles, what we do is we create turbulence and they are brought back into the suspension. So in case of Nepal, we have many swamp wells which are used to take water from the river bed and lift them to supply to the other people. So in that case, how swamp well works is that it filters there is a groundwater flow from the river to the well section, and in many cases during the dry season the very fine particles they get trapped over the surface of the river in the coarse bed. And then what happens is your permeability decreases and you have less infiltration, and that causes a problem in the discharge capacity of your well. So how we can like solve this problem is like exactly how the scientists have been solving the salmon problems. So what we can do is we can create an artificial turbulence in the river and then agitate those particles and uh, do not let them settle in the coarse layer. So how we can do that? In river there are yearly floods which do this naturally, but in case of low flow season you don't have flood. So what you do is you place some structures, or like you place structures in the river which creates obstruction in the flow and it generates turbulence. That's like a good example of application of the turbulence modeling, or the idea of the turbulence in case of in context of Nepal. Yeah.
Okay, sir. Khem, sir, would you like to add anything more on this on turbulence research? Khem, sir?
Yes,
Yes.
uh,
From your
turbulence.
side? Yeah.
Actually, turbulence has many applications worldwide,
Mm.
and turbulence flow can be used to study the stratified flows, stratified based on different density fluids, which can give important results and applications.
Okay,
Yes.
sir. Yes, yes. Now, Naresh, sir, would you like to add anything more on these questions relevant to environmental flows?
Yeah, I'm not a turbulent guy, but
Yeah,
I
but
have
you
deep
can
knowledge
ask.
about
Yeah, yeah,
turbulence. But I have one question, like very basic question, like
yeah.
how turbulent flows start. I want to start from here, like how the turbulent flows start. Like I think it's a
Uh,
like very simple question maybe,
Yeah,
but
yeah.
like I want to know like how the
Uh,
turbulent flows start. Can
Ankit,
anybody guess this question?
I would like to explain this answer through by Ankit, sir. Ankit, sir.
Actually, the turbulent flow start when the disturbance occur. Like in a first, it is the turbulence is created by increasing the Reynolds number. That is, increase in the inertial force or increasing the velocity. And second, the free stream turbulence, which is the artificial creation of turbulence. It is through the use of different grid or a turbulence box in which the turbulence is created. If we can see how the turbulence start in these two aspects, is that one in one aspect, it is because of the inertial force, and in second, it is by the uh, disruption of the flow by the external source or by using the external device to create a turbulence.
Okay. Uh, Ravi, do you have any, any queries regarding the turbulent flows to discuss here? Ravi, would you like to add anything more?
I think Robbie is not in the meeting. I think something problem with him. Yeah.
Okay, so we are at the end of the this session, and now
I, I I would like to like add here
yeah.
something.
Okay, sir. Please.
It's kind of like state of the art also, but I'm not that good in turbulence and how it is solved. But a recent trend has been like, for example, the flow of fluid is defined by the Navier-Stokes equation. So the recent trend is like since in Navier-Stokes equations, like turbulence parameters are very difficult to exactly estimate or to exactly predict. So what researchers are doing is that let's protect the physics in the flow and also like the unknown quantities or the turbulence parameter they are estimated using machine learning. So like if the presenter has any thoughts on that, I think this has been very like recent trend and is growing very fast. I think they say that like if you could do that, it is like competitionally very fast or something like that. So like, do the presenter have any thoughts on that?
Yeah, I have one thought that if research is based or similar to the research that is well studied, if we get a historical data or the research pattern, and we can create a specific AI model. And by using the AI model, we can have to predict the flow parameters. And this will be done according to the complexity of the flow. If the flow is more complex and require a more expenditure, then it is difficult to find the historical data for the to make a numerical model. But if we able to make a machine learning model by using the various data, we can incorporate that into our simulation, and we can it will be helpful to predict the turbulent effect or any effect in our numerical simulation.
Okay, sir.
Thank you.
Now I would like to conclude our the this webcast session. We have successfully discussed on the turbulent flow, Reynolds decomposition, turbulent fluxes, scales of turbulence, Kolmogorov scales, how turbulent fluxes emerge from the Reynolds decomposition. Similarly, which model is best for the sediment transportation and different turbulent models. And we have also discussed the different several questions relevant to the turbulent flows. And now I would like to thanks our chief presenter, Mr. Ankit Gautam, and all the six panel members. I would also like to thank them, and also I would like to thanks the audience for kindly listening to our kindly attending our webinar session. Uh, Now, is there any questions or anything? If you wants to add or ask, then you can just message us. Uh, we will also we are planning for the next webinar. I think we will very soon conduct our next webinar related to snow hydrology, and also we are also thinking of I think the uh, webinar on webinar by expert on the hydraulic structures, design of hydraulic structures. So that's all. Thank you all. Now I would like to host to end the meetings. Parthi sir.
Hello.
Mm,
Do you hear?
now you can stop the recording.